So yeah, we continue our discussion from the other night. So just want to make sure that this time around everything is okay. Not this. So yeah, I think the audio is all okay, and I hope you guys can get me just fine. Okay, so we now want to look at the application of conic section, polar coordinates to conic sections. So we now want to see how we can express conic sections in polar form. So in the previous live session that we did, of course, there was a glitch there, so I had to redo that video. So the link is in the description if you want to see that. We did work out this question. We saw the solution to this question. We also saw the solution to this question. And one other question that I included in the recording that I've just uploaded, I think I uploaded that recording a few minutes ago. I also included the solution to this question. So you guys can try out this question and see if you can express or show, convert this polar equation of an ellipse that is centered at the origin with the vertical focal axis. Can you show that it can be written in this form? So I hope it is clear. If it's not clear, that is r squared is equals to b squared over 1 minus e squared sine squared theta. So try to see if you can work out that. So this is coming from a past quiz paper, so you can try it out. Then you can compare your solutions with what I did in the recording. So the recording, the link again is in the description. You can look it out. This is going to be the last example in that video. So in tonight's video, what we want to now look at are equations of conic sections. So we're going to see how you answer questions like this one here, which carries 5 marks according to this, and something like this again. That's another question that we're going to describe. And I'm also going to see this and this, and we're going to look at this one. So we might not do all of them, but we're going to do a good number of them. So you guys look out for all that. So this is what we are going to do tonight. So all this this writing, of course, is from the recording from the previous session. So now I want to see equations or polar equations of conic sections. Okay. Now, how do we approach them? Well, the easiest way to actually understand what is happening here is to start with a parabola. So if you have a parabola of this nature that opens to the left, now we pick the focus to be somewhere here. And what we're going to do here is we're going to deliberately just assign this focus to be at the origin of this parabola. So we make it such that let me move this line instead. I think this line is fine. Okay, so I want to make it such that the origin of our coordinate axis is right along the focus of this parabola. With this in mind, we then want to make a few deductions. We want to convert this or relate it to polar coordinates and see the expressions that will arise. Of course, in polar coordinates, we just want to work with the radius r and the angle theta. So I want to be able to describe points about this parabola in terms of r and theta instead of x and y. So how do we do that? Let's pick a point that is somewhere here on our parabola. So let's label this point as a point P. So in terms of its x and y setup, this point let's say in polar coordinates, of course, this is going to be at a position r comma theta, where r is the radius from the focus to that point, and then of course theta is the angle we have to rotate it from that point. So that is where our theta is. Now, of course, you have to see that there are a few things that we can actually establish here. For starters, if let's say the directrix of this parabola is somewhere here, so if this is where our directrix is, now let's say the directrix is at a distance from the origin to this point that is at a point x is equal to k. So in other words, we're saying the distance from the origin here to where the directrix is, that is just some value k. So if we picture that point P, its distance as in horizontal distance up to where our directrix is, let's say at this point, this is at a point D, or the origin, let's take the origin to be at a point O. What you have to then see is that the distance from P to O, or OP, this distance can just be seen as equal to the radius, while the distance from P to D, this distance, we can actually write an expression for it. Well, to write an expression for the distance from P to D, notice that we can just first identify what the distance from here to here is, and then subtract this distance from the distance from here all the way up to there. So in other words, this distance, this smaller distance can be expressed in terms of r cos theta. It's just if this of course was a smaller triangle, this is going to be r cos theta. So in this distance, remember this is k, so you can express PD in terms of the full length, that is k, minus r cos theta. Now what you have to see here is this value of k, it's just the distance from the focus of this shape all the way up to the directrix. So it's not necessarily the distance from the center of the conic or what, it's the distance from the focus of the conic section up to where the directrix is. With that in mind, this leads us to one simple expression, because from here it follows that we can easily say that from here we can easily relate these two. We can relate the PO to PD, and if we were to come up with the relationship here, notice that we're going to easily say that PO will be equal to the eccentricity then multiplying PD. But since we already know what PO is, this is just r, and the eccentricity is here, PD on the other hand, this is k minus r cos theta. So we come up with this relationship. Now we want to write this expression in terms of r. So how do we do that? We distribute the eccentricity there. We're going to have r, then ek here, minus, again we're going to have that's that. We're going to have er, then cos theta. We group everything that has an r on the left hand side. We end up with r plus er cos theta equal to ek. Okay, so just a minute, let me take care of this. Okay, this should be okay now. Okay, so this will be equal to ek. Now from here we factor out the r, so we're going to have r here, so this is going to be 1 plus e cos theta equal to ek, so that in the end we end up with an expression of r that will be equal to ek over 1 plus e cos theta. Then this becomes an expression that relates r, the eccentricity, the distance k, which of course, as you saw, is from the focus to wherever the directrix is, and then of course to the angle of rotation theta. Now this expression that we have just derived, don't forget what it is for. It is, in this case, for a parabola or a conic that opens to the left, or we can say that it is a conic where the directrix is to the right of the node. In this case, we are picking this to be, we can even argue to say that it's to the right of the vertex. So it opens, the directrix is a vertical line, and it is to the right of the vertex that is here. So you can easily see this expression. Now, we can easily derive the other expressions, but you can just make a few conclusions here. If let's say we had a similar setup, let's say a parabola again, that opens in this manner, but now with the directrix being somewhere here, would still end up with a similar expression. Of course, if we chose again to say that the focus is right at the origin, let's say the origin is here, but in this case we're saying that the directrix is to the left of the vertex here. Notice that it will end up something like this as well, but the only difference is going to be the sign. So if it opens to the right and it is literally horizontal, opens to the right, we'll still end up with r, But this time we're going to have ek, and then this is going to be 1 minus, and then we're going to have e cos theta. So this is an expression that we are going to end up with. Now, if we were in the y-axis, if it was opening up or down, notice the trend here. When it is positive, it's opening to, when it's positive and it's a cos, it opens to the left. When it's negative and it's a cos, it opens to the right. But when it is, let's say, positive and it is a sine, e sine theta. In this case, what we expect is that this now, because of the presence of sine, you expect that this is going to be opening either up or down. The presence of a positive, notice again, relate to this, when it was positive, it opened to the left. So we can make the same conclusion here. Since this is positive, you expect this, first of all, to be in the y-axis, open either up or down, but being positive, it will open downwards to the negative. So it will open something like this. You expect the directrix to be something that is above that node. So this is what we expect. And in the same manner, we can also make the same conclusion for when or if this is negative, for r is equals to ek over 1 minus e sine theta. So again, we're saying because it's sine, it's opening either up or down, but because it's a negative, it's opening upwards to the positive. So you know to say it's going to open upwards, and the directrix is going to be below that node. So it's going to be something like this. Now, of course, the types of conics that are going to arise here, they're not always going to be parabolas. You don't confuse the two. We're only using one part of the conic section, and this part that we are focusing on, it's the one whose focus is literally at the origin. So this is literally the part that we keep focusing on. But of course, depending on the conic section that we're dealing with, it might be that if this is an ellipse, maybe it gets to be complete the other side. But the only piece that we are interested in is the one whose focus is exactly at the origin. That's the one that we keep describing by opening up or opening down and so on. Okay, with that in mind, then how do you identify them? How do you conclude that what you're dealing with is an ellipse, or what you're dealing with is maybe a parabola, a hyperbola, and so on? Well, that brings about the, it asks you to remember what eccentricity is all about. So if you recall, eccentricity by definition, how do you find the eccentricity of a line? So eccentricity, we have c over a. So this is what the eccentricity is. And in this case, we know to say if the eccentricity is, let's say, okay, you have to use the eccentricity to actually specify what the shape is. If e, for example, is equal to, let's say, 0, you have to know what shape you're dealing with. If e is equals to 1, you also have to know what shape that is. And if e is equal to, let's say less than 1, you have to know what that is. And if e is greater than 1, you have to know what you're dealing with. Let's look at an example here where we are literally trying to identify what we're dealing with based on the polar expression that we've been given. So let's say we have something like, in this case, let's say we have this example 1. And in this example, we have to identify. So we want to identify and sketch. And sketch the graph of the polar equation. Okay, say this is what we have, the polar equations. Let's start with the first one. And for the first one, we have a is equal to, so we have a, r is equal to, let's say we have 32 here, and then this is over 3 plus 5 sine theta. Okay, so I'll keep checking the comment section in case you guys have a reaction. So don't hesitate if you've got something that you want to add. Just comment it in the comment section. I'll keep checking that part as well. Okay, so let's proceed. So let's say we have an example like this one. And the question is saying, identify the conic section and then sketch it. So in this case, we only have to compare it. First and foremost, look at this, they're using sine. So because they're using sine, when it comes to sketching it, you know it will open up or down. But what shape are we dealing with? To identify the shape, we compare it. The one that is positive and with a sign, it looks like this. It's going to have EK on top, and it's going to be over 1 plus, and this is going to be E here, and then sine theta. So if I compare this expression to the one that is given, you quickly notice a few similarities here. First of all, they all have sine, but the difference, the key difference here is that you notice that in the standard format, this must be a 1. But when you look at this, this is not a 1. So that is your starting point. You want to ensure that this is a 1. So how do you do that? Divide everything by the 3 there. So that expression now becomes, the numerator, when you divide it by 3, it becomes 32 divided by 3, then over the 3 itself divided by 3, that would be a 1, plus, now you're going to have 5 divided by 3. So this becomes 5 over 3. Then you have sine theta. Now, when you look at this expression, now this expression looks more like the standard format, where this is a 1, this is a 1, you have a plus here, you have a plus here, this is 5 over 2, that's one thing, and then you have EK on top. So this has to represent EK. So based on this format, we can then try to identify what shape is, what shape this is. So if we compare it, you see that this, the coefficient of the sine theta, represents what E is. In this case, the coefficient is 5 over 3. So in this case, we conclude that E has to be equal to 5 over 3. Since E is equals to 5 over 3, and we notice that this E is greater than 1, then we can make a conclusion on what this is. You know, to say if E is greater than 1, then this has to be a parabola, a hyperbola, I mean. So we conclude that the conic section here is a hyperbola. So it's a hyperbola. Now, once we have specified where that this is a hyperbola, we can also specify how it behaves. Of course, here when you look at this being positive, you know to say it opens facing in the negative direction. So we expect that the directrix is going to be something like this. But of course, we know to say a hyperbola will have two pieces. One piece, if the main piece, this piece that I'm drawing here, it's the piece whose focus is at the origin. So if this piece opens down, then of course, being a hyperbola, you expect that it's going to have another piece that will most likely go something like that. But I'm just saying, when we say it's opening down, we're focusing on the piece whose focus is centered at the origin. Okay. Now, with that in mind, we now have identified what this conic is. The next part is to try to actually sketch this conic section. Now, how do we sketch it? Well, the next thing that we need is to identify how far the directrix is from that focus. Now, of course, if you recall how we derived that the earlier expression, we said K was the distance from the focus of this main piece to where the directrix was. So you can easily find what K is. So if we come back to our question, we see to say that the top part is EK, since that's what is here. So in other words, in this case, our EK is actually equal to 32 over 3. So you have 32 over 3. But we have just found what E is. E is 5 over 3. So you have 5 over 3K equal to 32 over 3. At this point, the 3 and the 3 in the denominator can cancel out, so that if this and this eliminate out, you remain with 5K equal to 32, so that in the end, K is just equal to 32 over 5. So this is what our K is. Now, once you've done this, you can actually even start trying to sketch your problem. So of course, Start with the main one. The main one in this case opens downwards. So the origin, of course, has to be at where the focus is for the main one. So you know it opens down. I'm just going to put it as something like this. Okay, its focus is literally right here. Now with this done, we now also know what what k is, and k is 32/5. Now if we're going to sketch this, of course we need two parts. We need, being a hyperbola, we have one part facing down, the other part has to be up. We don't know exactly where that is, but even for the piece that we have sketched, we can actually try to make a few conclusions already. We can try to determine what this point at the top is going to be, what this vertex here is going to be. Now, how do we determine what this vertex is going to be? Well, you have to keep playing with what your arrow is going to be. You know, to say, if I was to just go back to the basics, this is where arrow is, and you have the angle coming in this manner. So if, let's say, this is opening in the y-axis, what you want to focus on is the angle when arrow. You want to focus on what arrow is going to be when the angle is equal to 90 degrees, or when the angle is equals to pi/2. Why are you focusing on that? Because you want to find what the radius is going to be when the angle here gets to 90 degrees. The value of r will actually be what the vertex at the top is going to be. So with that in mind, I want to know what r is going to be when theta is 90 degrees. So we can say for theta equal to pi/2 or 90 degrees, what will be our r? So to find this value of r, we go to the original expression. And our original expression was, what was that? That was this expression here. Want to find what r is going to be when theta is 90 degrees. So this is what we have. Okay, so if theta is 90 degrees, notice that this expression becomes 32 here over, we have 3 here plus 5, then we have sine 90. Sine 90 is a 1 here. So sine 90 is literally a 1. So for theta equals to 90, this is going to be 1. And then in the end, we're going to end up with 32 over 3. 1 multiplying 5, that's just going to be 5. So this becomes 32 over 8. And we know 8 going into 32, this ends up giving us a 4. So we end up with r being equal to 4. What does that imply? It then implies that for this shape that we have just drawn here, for this shape, too much again. Okay, for this shape, at this point, this is actually going to be a point on the x value. This is 0 on the y value. That is going to be a 4. So that is 0,4. We have even determined what one of the vertex is going to be. But again, don't forget, this is a parabola, not a parabola, a hyperbola. It has two pieces. It will have this, it will have the other part on top. So remember, we had our directrix as well given by k. So our directrix was somewhere here. We can literally just approximate where it is. So we had it as somewhere here. Instead of broken lines, let me just use a solid line. So it was somewhere here. And you know the equation for this line, it was at the point where k was equals to 5. So you can say this is for y equals to, that was 32/5. So that is y equals to 32/5. Okay, now with this done, we want to determine one other thing here. We also want to determine where the other piece is going to be. Well, there are a number of ways we can actually try to predict that, where the other piece is going to be. Among them, we can just look at a few distances. We know to say, if let's say, we can just, let's do this. Let's extend this graph so that it caters for the other part. Okay. Let me make this smaller. Okay, so yeah, I think this is better. Okay, nice. Okay, so we have one piece already drawn. Now we need the other piece of our hyperbola. We know to say the other piece, if we were to sketch it, we know to say it's going to go something more like this. Okay, let's make it a little bit smaller. Okay, we know to say it's going to be a little bit like this, but a few things stand out here. First and foremost, the distance from here to here has to be the same as the distance from here to this point. Apart from that, the distance from this point to where the focus is going to be the same as the distance from here to where the other focus is. So let's say the other focus is somewhere here. So since this, we already know where this, sorry, that's not the focus, that's the directrix. So, sorry, this is not the focus, that's the directrix. The focus is somewhere else. Let me actually try to show that the focus is somewhere else by shifting this one a little bit up. Okay. So let's say this is what we have. This directrix, we're going to have another one somewhere on top. So we have something like this. And so that our center, is somewhere here. Okay. Our center is somewhere here. Okay. Now, there are a number of ways that you can actually determine where this center is. But before we get there, I want you guys to just look at one thing here. Okay. Okay. So before we get to those, I want you to see one thing. We already have our E, and our E was equal to where did we get our E? Our E was 5/3. Yeah, our E was 5/3. 5/3, that was our E. And then we also have our K. We've ended up finding our K as, and that was, where is our K? Our K was 32/5. Okay, yeah, that was where our K was. Now what we want to do here is to find where the center is, find where the other focus is. Now, how do we get to actually do that part of the math? Okay, so just a minute, let me just put one thing in place. Okay, so I'm back. Right. So to do that, this part I already did for you for theta is equals to 90 degrees. Well, you have to do about 4 of them. You have to do when theta is 0. We've already done when theta is 90 degrees. You also have to do when theta is 180. You can also do when theta is equals to 270. So these are all the 4 that you can do here. We've already done for this one. You can also do for when theta is equals to that, or it's equals to 0. But the interesting ones, for the one that opens in the y-axis, will actually be for 90 and for 270. This is going to be what the interesting ones are going to be. So you want to determine what r is going to be for the angle theta equals to 270. So these are going to be the interesting ones for you to focus on. Okay, now how do you actually do it for this one? Well, for 270, this is basically the same as that's 3/2 pi. So in this case, you're going to have again the standard expression. R is equals to, we had what was the original one? Okay, that was 32. Was it 32? Yeah, I think it was 32/3. Just copy it again. Okay, so we have this one. But now the angle we want to use 270. So we have 270 here. So in this case, what are we going to have? This is going to be 32 over, this is going to be 3. So sine 270, this is going to be -1. So this becomes -5. And then, yeah, so this in the end becomes 32 over. And then when we plug in the value here, when we subtract here, this ends up giving us -2. So that in the end, yeah, that's a -2. Okay. So that in the end, this ends up giving us this into that. Is it a 16? Yeah, this ends up giving us a -16 as our error. So for this point, we find it at -16, comma, I had the angle in radians. That's 3 over 2 pi. So over 3 over 2 pi. But what you have to see here is this. What you have to see here is this. The values that we have here, I did put a 4 here. I did put a 4. We'll come and check it out. So what you have to see here is this. What you're plotting is actually the XY plane. I should have also mentioned this earlier on. So what we're plotting, this is the x-axis, and this is the y-axis. So what you're plotting is on the XY plane, but the values that I'm finding there are y values and as in our r values and theta values. What I then have to do is I need to find the corresponding x values and y values. For example, in the first part, we found x was not x. We had when at first we had that was where we found the 4. Where was the 4? It was here. We found r was 4. R was 4 when theta was pi over 2. We can literally find the corresponding x value and y value for these angles. So to find the corresponding x and y value, you can just use that standard expression. X is equals to r cos theta. So that x will be r, the radius is 4, cos theta, that's pi over 2. So this is going to be cos pi over 2. So we know to say this is going to be a 0 because cos 90 is 0. So this is going to be, the x value is going to be 0. So in Cartesian coordinate, this is going to be the same as 0, comma. How about the y value? The y value is r sine theta. In this case, it's going to be 4. This is going to be 4 sine 90. And sine 90, here I wrote it in radians, still 90, of course. Sine 90 is 1. This is going to be 4. So this is going to be 4 as in 0, 4. This is why it still comes out to be this point. I should have just pointed it out when I did that. So for the next part now, I've done for 270, and for 270 we've seen that when the angle is 270, we end up with r being 16. But now I need the x value. The x value, again, you can still do the same thing, and what you notice is that for this part, we can say again r cos theta. R this time is -16, and cos 270. 270 will still be a 0, so this will still be a 0. In the same way, you find your y value is going to be 0, comma. Your y value is going to be positive because sine 270 will be negative, so this is going to end up being positive 16. So the other point ends up being, for, of course, r being 16, r being -16, and the angle being 270, you end up with a corresponding Cartesian point of 0, 16. So this is going to be the point in Cartesian form if this is the point in polar coordinates. So now, of course, if you get this point, then what this is actually telling you is the vertex. Notice what we're doing here. We're literally getting what the vertex is. We're trying to find where r will point for respective, where r will be for respective angles. So if, let's say, the angle is 90, we found this point, and this point was 0, 4. The corresponding one that we have found for 180 is going to be this point here. And we start to say this point is going to be 0, 16. So we have found where the other vertex is going to be. Now, with the vertex found, you can easily predict where the center is, because you know to say for the one down, the distance from here to here is a 4. And you know this distance will be the same as the distance from here to where the other foci will be. So if the distance down here is a 4, then the distance up here will also have to be a 4. Since this is at 16, just add 4 to 16 and you get this as a 20. So the other focus is going to be at 0, 20. Now, how about the center of the whole thing for this hyperbola? Where will the center be? Well, for the center, all you need is the distance from this point, one vertex, to the other vertex. Since this is at 16 and the other is at 4, you can conclude that the difference between them is going to be 16 minus 4, which ends up giving you a 12. The central point will be when you divide 12 by 2. So if you divide 12 by 2, this ends up being, it will give you a 6. So to find exactly where this is, you know to say from here to this vertex, it's a 6, but you are already 4 above the origin. So just add the 4 with the 6, and this is going to be at 10. So if we're going to make conclusions for this one, here's what we're going to conclude. For that hyperbola, the center is at 0, 10. When it comes to the foci, of course, we have two of them. The other one was centered at the origin, so we're going to have 0, 0 for that one. The second one is all the way up at 0, 20. Then next, we have the vertices. For the vertices, what did we have? The other one was literally at 0, 4, but the other one was all the way up, and it was at 0, 16. So we have a few more things that we have to specify, and these are going to be the asymptotes. Being a hyperbola, we need to specify where the asymptotes are going to be. Now, to find the asymptotes, of course, you have to get the original expressions. We already have our A. Where is that? Okay. So we have... Okay. So we can easily get our A, our B, and our C, A, B, and C, by looking at our diagram. We know to say A is the distance from the center of this, this conic to the vertices. And in this case, the distance is a 6. So in other words, our A is a 6. How about our B? Our B, of course, here B will not be necessary. All we need is A and C. So C is the distance from the center of this this conic section to the foci. So in this case, we know to say that was a 10, a whole 10. So from this point to that point, that's literally a 10. So this is a 10. So we have our A, we have our C. We can easily calculate what our B is. A hyperbola, of course, you know what you have is as a 6 and a 10. Which one is the 6? Which one is the 10? So A is 6, C is 10. Okay, so A is 6, C is 10. So what we're saying here is to find B, you know C squared for a hyperbola is equals to A squared plus B squared. So that from here we can easily get what B squared is. It will be C squared minus A squared. And our C squared is 100. Our A squared is 36, so that this is 64. So our B squared is 64. Being a hyperbola opening in the vertical axis, we know to say it's going to be y minus, and we know to say in this case, the center is shifted in the y-axis. So the y value has been moved vertically upwards, 10 units, of course, up. So we can say this is y. I'm writing the expression in Cartesian form. So it's going to be y minus 10 squared over the value of A. And the value of A is 36, A squared. Then minus, since we are in the vertical axis, this is going to be minus. The x has not been shifted, over b, and b squared is 64 is equals to 1. So to find the asymptotes, just make this a 0. We're going to have y minus 10 over 36 squared. If that is a 0, then this will be equals to x squared over 64. Then solve for y. In this case, we're going to end up with y minus 10 squared equals to 36 over 64, and then x squared. From here, of course, square root both sides. You're going to have y minus 10 is equals to the square root, of course, plus or minus, of 36 over 64 x squared, so that this becomes y is equals to, when I square root here, this is 6 over 8 x. This is plus or minus, then plus 10 here. So our equations will be y is equals to 6 over 8. 6 over 8 we can simplify. This is 3 over 4 x, then plus 10, and the other one is going to be y is equals to minus 3 over 4x plus 10. So these will be the equations for the asymptotes. So if we came here, we can easily predict the one with the negative gradient will have to be the one going downwards like this, and the one with the positive gradient will have to be the one going down like that. So of course we can move these around so that they just pass at the origin. Okay, somewhere there, and this one as well, somewhere there. Okay, you can easily label the equations so that you know exactly what is what. Okay, so we have sketched our hyperbola. I hope you guys are able to follow through this. We still have a few more examples to go through so that you guys easily get this. Let's do one more example. So I'm seeing the comment section, there are no comments, so we seem to be okay. So let's look at B of the same question. So again, we're still trying to do the same thing, but in this case, let's see the question that we're going to do. Now what we have is R is equals to 15 over 3 minus 2 cos theta. Again, want to do the same thing. Want to identify the conic section, and we also want to sketch it. So to identify it again, we compare it with the standard form. I'm seeing a cos here, so we're going to be dealing with the horizontal axis. And then I'm seeing a minus here, so it's opening to the positive x. So the standard form has to be ek over 1. Don't forget, this is always the 1, the first one. Then minus e cos theta. So when I compare, this has to be a 1. It's a 3 currently. So let's divide through by 3. We end up with r is equals to, it's going to be 15 divided by 3, which is just going to be a 5. Then 3 by 3, that's just a 1, minus. Then we have 2 divided by 3, it's going to remain, and then cos theta here. Once this is done, again, if we compare, it implies that the coefficient of the cos has to be our e. In this case, it's the 2 over 3. So we conclude that our e is equals to 2 over 3. And when we see our e being 2 over 3, well, this is less than 1. And we know to say when e is less than 1, it implies that the conic section we're dealing with is an ellipse. So this has to be an ellipse. Okay, so just a minute. Yeah, this is an ellipse. Okay, so once we've made this this conclusion, we can then move on to start seeing what we expect. So again, this being a negative here, we expect that the main one opens to the right. So if I was to put my coordinate axis like this, so our side of interest is going to be something like this, with the focus at the origin. So this piece of the ellipse whose focus is at the origin opens to the right, because that is a negative. If it was a positive, remember that's the piece that we used, it opens to the left. So that being a negative, we know that this piece whose focus is at the origin opens to the right. But we know it is an ellipse. So being an ellipse, we know to say its complete form is going to be something more like this. So this is how the complete form is going to look like. But don't forget, when sketching it, we're looking at it as if it's just a one piece of a parabola. Or yeah, we're looking at it as if it's one piece of a parabola. We're not looking at the rest of it this side. We're more like just focusing on the other piece this side, so that it's the one that I keep talking about, say it opens to the left or to the right and so on. In this case, this piece opens to the right. In other words, opening to the right just implies that the directrix of this piece is going to be more like this side. Okay. Now, again, this is at the origin, so I have 0, 0 here. But we need to identify a few things. We need to identify what this is. We need to identify what this is. We need to identify what the center of for this ellipse is. We also need to find where the other foci is going to be. Now, how do we do all that? Well, it's literally the same as what we did in the previous case. But having already found what E is, so we saw that E was equal to, that was 2 over 3. So this part is already sorted out. But now we need to make predictions. To find the vertices, we do what we did previously. Again, you want to check for angles equals to 0, and then theta equals to 90, theta equals to 180, then you have also theta equal to 270. But you don't have to do all of these. What you can just focus on here is you can just look at, to find the vertices here, the value of A, which is going to be the value of A. This one is in the horizontal axis. So in the horizontal axis, you are interested in theta being equals to 0 and theta being equal to 180. For the previous example where we had the hyperbola, which was in the vertical axis, notice that we ended up focusing on theta being equal to 90 and 270. So you can be using this trick to simplify your life. So here we're dealing with cos. I'm working with 0 and 180. So let's see what we're going to end up with. So our conic section was given by this expression. So I'm just going to copy the expression again. So I'm going to play around with this expression for those two selected angles. So I want to find the value of r when theta is 0 and also when theta is 180. So for theta equals to 0, I'm going to have r equals to 15 over 3 minus 2. So the first one, cos theta is 0, so this is what I'm going to have. This is going to be 15 over 3 minus cos 0 is 1, so this is minus 2. So this ends up being a 15. So r is equals to 15. So what does this imply? Well, now we have r, which is r comma theta, which is now being represented by 15 comma 0, 15 comma 0. But we don't want r, we want x comma y, because what I'm having here is the x-axis and the y-axis. So to easily translate, we can just say that, okay, our x is r cos theta, so r is 15, the angle is 0, so this just reduces to just a 15. So our y, of course, when you do the same thing, this is going to be 15 sine 0. Sine 0 is 0, this is going to be 0. So in Cartesian coordinate, that is going to be 15 comma 0. Okay. Yeah, so this is what we have. Okay. So we can do the same thing for the other points as well. I said we're going to try two things, 180 and 180 and a 0. We've done for 0. Now, how about for theta equals to 180? For this case, again, we have r is equals to 15 over, then we have 3 minus 2, then we have cos 180. Cos 180 is negative 1, so this is going to be a 15 here over 3, then minus, so this is -1, this becomes +2, and this is going to be 15 over 3 over 5, I mean 15 over 5. Then 5 into 15 goes 3 times, so you get r is equals to 3. So in terms of r comma theta, we know to say this is going to be 3 comma 180 or comma pi. Now we want this in Cartesian coordinates. In Cartesian coordinates, x is equals to r cos theta again, so that your r is a 3, then cos 180. So this becomes cos 180. When you bring in what cos 180 is, that's a negative, so you end up getting -3. And when we try for y, r sine theta, this is going to be 3 sine 180. Sine 180 is 0, so this ends up being 0. So you have -3, 0. These are the vertices. So playing around with the angles actually gives you the vertices. So one vertex is at -3, 0. So if you look at this, it can only be one. When you look at this diagram, it can only be one of them. So in this case, this one here has to be at -3, and the other one here has to be at 15. Now, with these found, the next thing that we can do here is we can actually even predict where our center is right from this point, because we know our center has to be exactly midway between the -15 and the 15 here. So we can literally predict where our center is going to be right from this stage. But before we get there, let's just see if we can actually find a few other things just from here. Okay, so yeah, let's see. Can we actually find our center? The distance from -3 all the way up to this is going to be about 18. So 18 halved, that's about a 9. So in other words, we're saying it's a 9 from here all the way up to the center. So if this is a 3, then from this point marching up to the center, it has to be a 6. I hope you're seeing what I'm using here. From one edge all the way up to the other edge, I've just done 15 minus 3, it gave me 18. That's the distance. So up to the center, I have the 18, it has to be a 9. So to move from -3 to the center, I have to move 9 steps. But since to move from here to here, it's 3 steps, it implies that from here to here, it is 6 steps. So this tells me to say that the center for this ellipse is actually at 6. So I hope you've seen what I've used here to get that center a little bit quicker. We could have also used the other methods, finding A, finding B, and so on. It will also work here. You can try it out. Okay, I don't want to remove everything. Okay, so we have found where our C is. So our C is right at 6. Okay, now with our center found, we now want to find the distance. We want to identify where the other focus is. Want to find where this point is. Well, with the center found, we don't actually even have to do a lot of math. Why? Because we already know from here what this distance is going to be from the center to one of the foci. Because we know to say this distance here has to be the same as this distance. So if this side, this is a 6, it only makes sense that this one here also has to be a 6. So if we know this, then we can easily say that, okay, since this is at 6, to 6, add 6 again, so that you end up with what this is going to be, and we conclude that this is going to be 12 here. So there we have it. We have sketched our graph, we've identified what it is, and we have also labeled all the important points here. So I hope you guys were able to easily follow through this one. If you wanted to identify what this point is and what this point is, then you can play around with what the y value is going to be when theta is 90 and also when theta is 270. But the most important ones are the ones we have done here. Okay, so let's see if you guys have any questions in the comment section. Okay, there's nothing there, so we can proceed. So this is one example. I hope you guys were able to keep track with this one. So now we can move on to look at some exam questions or some assessment questions that that I was able to find. So let's see. Funny thing is, the last example we are from working out, it's actually coming from one of the assessment papers. And let's see if we can find it. Is it here? Yeah, this one. So this was actually a test one from some time back, and it's the one that we are literally from doing. In this case, they were saying identify the conic section, find the vertices. Well, we did find the vertices. Find the center. I hope you remember. One of the vertex was at -3,0. The center was at 6,0, and then the other vertex was at that was it 15? Yeah, it was 15,0. Then the foci, for the foci we had two of them. The other one was at 0,0, and the other one was at 12,0. And then the other one was the equation of the directrix and sketch the graph. So we sketched it. The only thing that we didn't do perhaps is getting the equation of the directrix. But of course, the equation of the directrix is given by the value of k. And I think we're able to get what k is by just equating ek to what the numerator was. Yeah, I think the numerator was 5. Yeah, so equate ek to 5 and then solve for k. We can also do it. If you guys want me to do that, you can just comment and then we'll look at it. Okay, now let's look at a few more examples from this same from these that were gathered. We have this one here. This was with that was 11 marks. That's a lot. Okay, is this just 11? No, looks like there's more. I'm seeing this one here, but let's see what you had to do here. Or we can do them in order. Okay, doesn't really change a thing. Let's do which one was that? This one. Let's look at this one. Okay. So let's begin. So we have this expression. Again, they're saying a conic section with one focus at the origin. See, now they're specifying they want one focus at the origin is given by that expression. Identify the conic section, and after identifying it, next find the coordinates of the center or the vertex of the conic section. Next, sketch the graph, hence or otherwise sketch the graph. Okay, so now they're just making it different. This is a different one, and then you have a different here. The difference, of course, is here this is positive, this is negative. Now this is negative, this is positive. Okay, so there's not going to be much to do there to sketch the two graphs. Let's see how it goes. So you have r is equals to, we have a 40 here, then divided by, then we have 4, that's -7 sine theta. -7 sine theta. Okay, so again, seeing that this is a negative, I know to say the main one opens in the positive one. I have no idea what it is first, but let's see how it goes. What they want us to do in the first part is identify it. To identify it, all I have to do is compare it with the original shape. So the original shape, seeing a sign there, this is going to be r is equals to ek over 1 minus e sine theta. So I just want to make sure that this is a 1 here. So I'll divide everything there by 4. So it becomes r is equals to the numerator divided by 4. That's 40 divided by 4 over 4 over 4. That's a 1. Then minus 7 over 4. 10 sine theta. 40 over 4, that's a 10. So we're going to end up with 10 divided by 1 minus 7 over 4. Then we have sine theta here. So from here, we can easily get what our E is. Our E is 7 over 4. And 7 over 4 is greater than 1. So because it is greater than 1, we conclude that this is a hyperbola. So we conclude that this is a hyperbola. And of course, the other example that we did was a hyperbola. So I'm tempted to let this go, since we already saw how we approach a hyperbola. it's going to be the same things. Let me see if we can just do even B of this and then sketch it. You guys can finish up the other one. But it's similar, it's pretty much the same as the other example that we did. Find the coordinates of the center, the vertex, and of the conic section. Okay, let's see how it goes. Okay, so to find the rest of it, we're going to start playing with the angles. We know we're dealing with theta is equals to 0, theta is equals to 90, theta is equals to 180. Then the other one is theta is equals to, it's going to be 270. Since I'm dealing with sine here, we're going to stick with the ones that will matter for sine, which is 90 and 270. So in this case, we want to know what R is. Let me get this. We want to know what R is for angles 90 and 270. Okay, so what is R when the angle is 90? So when the angle is 90, R ends up being 40 over 4 minus 7 sine 90. Sine 90 is 1. This becomes 40 over 4 minus 7. 4 minus 7 becomes minus 3. So this ends up being minus 3. So if R is minus 3, now I want to know what X is. So I'm going to have X is equals to R cos theta. And then R is 40 over 3 negative. Then we have cos 90. Cos 90 is 0, so this whole thing becomes 0. How about Y? Y is R sine theta. R is 40 over 3. Then we have sine 90. Sine 90 is 1. Y comes out as negative 40 over 3. So the first vertex is going to be at 0, 40 over 3. That's the first one. Remember, this approach gives us the vertices. What about the other one? For the other one, we're going to do for theta equals to 270. So see again how I pick them. If I'm dealing with a conic that has sine, I deal with 90 and 270. If I'm dealing with a conic section that has cos, I'll go with 0 and 180. So I can even say if it's sine, if it's cos. So if it's sine, I'll go with this. If it's cos, I'll go with this. So these will be the ones that give me the vertices if I'm dealing with the respective angle, the respective ratio, I mean. So with that done, for theta equals to this again, I'll want to find what my R is again. So now I'm going to have R is equals to, that's going to be 40 over 4 minus 7. Then now it's sine 270. For sine, okay, let's go on with it. So this is going to be 40 over 4. 270, this is going to be negative now. So this will end up being positive 7. So when I add up, this is going to be 40 over 11. So this will be my R. With my R found, I can now get my X. X will be R, which is 40 over 11. Then cos 270. Cos 270 is 0. This will end up being 0. Y is going to be 40 over 11. Then sine 270, again 270 sine, that's negative. So this will be negative 40 over 11. What does this tell you? It tells you to say that now the other vertex is going to be at 0, negative 40 over 11. We have the vertices. The other one was here. The other one is here. With the vertices known, we can easily get where the center is. Because, check this, if we have, let's say, this is the conic, we know to say that being a negative, the main one opens up. So the other vertex was at, what was that? 0, we had 0, 40. The other one is 0, 0 comma negative that. I just want to make sure that everything I've done here is okay. So this was negative that. Oh yeah, this is negative, huh? This is negative here, so this is a negative here. That's what why I was coming here, because I know the origin being at one of the focus, I expected both vertex to be below that 0. So this is a negative here. So I hope you guys were able to catch that. And this one here is correctly a negative. So when I sketch this, the other vertex is at this point. This is at negative, that's negative what again? That's negative, I didn't write it here, negative 40 over 3. That's 0 comma negative 40 over 3. The other one, we can even put it somewhere here. And this one here, if we check what we're just from doing, it's negative 40 over 11. So this is negative 40 over 11. Okay, so yeah, let's see. I think this is going to be bigger. This is going to be relatively smaller. So I can swap these. This can go up and this can come down. Okay. So of course, getting where the center is, we know to say the center has to be exactly midway between them. So if you wanted to know where the center is, just add them and then divide by 2. So you can, of course, these are big numbers, so that I won't really get the exact values. So you can add them, then divide by 2. So I'll say minus 40 over 3 minus, I'm subtracting them, of course, minus 40 over 11, then divide by 2. What this would tell you is the distance from here to here. So once you have the distance from here, add it to the 40 over 11, so that it gives you exactly how far down you have to go to reach the center. So I hope you're seeing how I'm getting where that center is. So once you get the center, that's literally what they wanted you to do in the second part. They wanted you to get the vertices or the center, and then find the coordinates of the center or the vertices of the conic sections. So we already found the center. We also even found the vertices. So there is even no need for us to get everything else. It's for the second part, the third part, where they want us to sketch it. We've already done the heavy part. The only thing that is left perhaps is to specify where the directrix is, get the asymptotes as well. Then everything is sorted out. Perhaps we also have to identify where the other foci is. To get where the other foci is, if we know this is minus 40 over 3, we know to say to the minus 40 over 3, just say this is just going to be minus 40 over 3. Just add that. Perhaps let me do it like this. Let me bring the negative already outside. To find what this point is going to be, this point here, this point is going to be in the x-axis, it's going to be 0, comma, but in the y, you have to add. This is going to be negative, so let's say negative. Then it's going to be 40 over 3, the distance from the top all the way up to here, plus the distance from the other focus I'm going to use from here to here. Since from here to here, it's that minus 40 over 11. So just say plus 40 over 11. This will give you the coordinate of the center here. So notice that most of the steps I'm doing here, they are similar to what we did in the previous case where we had the hyperbola. That's why perhaps I'm reluctant to go all out to work this one out. But you guys can try to finish it and let's see what you get here. Okay, so we can leave this one here. If you guys want us to go all the way, let me know in the comment section. We can try to work it out also all the way. But the other ones that are here, I want to finish this as soon as possible. I have another class coming up. So let's see what else. Here, of course, they're saying discuss the conic section. And if you guys can see this properly, this is r is equals to 11 over, this is 1 over 2 plus 1 over 2. Then we have sine theta. So try to see how you find this. Of course, to discuss it, you have to identify the conic section. you have to find the center of the conic section, find the foci, also show where the directrix is and sketch it. That's how you discuss a conic section. So try to do that. Let me know in the comment section what you guys will identify as the shape of this one. What conic section is it? And then what else? With one foci, again, this is the same scenario. As you can see, we have negative 7. This is similar to the one we're just from doing. So won't really be much of a problem. And then find the coordinates of the vertex or the vertices of the conic section. Here, they don't even want you to sketch it. They just want you to identify it. So just in case you can't see this one, this is r is equals to 30 over 3 minus 7 sine theta. So of course, E is going to be equal to 7 over 3. So this again is greater than 1. So you can see this is a hyperbola. So it looks like they like asking questions on hyperbolas a lot. So this is the one we're from doing. And we also did this one. Okay, so we can end here. Let me know what you guys think in the comment section. If you'd want me to continue with the live series, just let me know and then we'll do another one next week. So we can end here. If you've got any reactions, let me know in the comment section. Otherwise, we'll see you guys in the next session. Enjoy the rest of your weekend.